Hello everyone, my name is Sejal Hemant Shetty. I completed my internship at MSc Information Technologies. Today I will be present my project IoT-Based Home Automation Solution. First, I will discuss what I have learned in this internship. Later, I will give the live demo of my project. So, let's get started. First, we will discuss about foundation proficiency in C and C++ for embedded devices. Before diving into solutions, it is important to highlight the foundational skills used. The core logic of system was to build using robust embedded C and C++. In C programming, we focused on critical practices like using pointers, null safety, to prevent memory issues, a fundamental requirement for reliable embedded debugging. We also leverage preprocessor directives like hash define for efficient comparable code. The system logic was primarily structured using C++ principles. We implemented object-oriented design OPP like encapsulation and abstraction to create modular reusable classes for handling sensor data and communication logic. The OPP foundation ensures the project is highly scalable and can easily accommodate new features without a major code overhaul. So let's see the project tools and its ecosystem. The project relies on three-part ecosystem. First is a development, second is a simulation, third is a connectivity, and we will see the key components. First is a development. The code is written using Arduino IDE, which is a standard environment for writing system logic in C and C++. Second one is the simulation. We use PicsimLab. This is our hardware-in-loop simulation tool. It allows us to safely test and iterate on sensor interfacing and microcontroller logic without needing physical hardware initially. Third one is a connectivity. The entire solution managed by Blynk IoT platform. Blynk provides the cloud server, the data streams, and crucially remote user interface on mobile application. The simulation focused on ESP-type platform interface with ultrasonic sensor for water level and temperature sensor. And here are the key components. First one is a microcontroller and sensor, which is a simulation focused on ESP type platform with an ultrasonic sensor and temperature sensor. Let's see next system architecture, the data flow. Here we use the four-layer IoT stack. The system architecture follows standard four-layer IoT stack, illustrating the data flow from sensor to user's phone. First layer is a reception means sensing. This is where we acquire data from physical environment using our sensor, especially the ultrasonic sensor for distance, level and temperature sensor. Second one is a layer 2 processing microcontroller MCU. The data moves to the microcontroller which executes our embedded C++ logic. Here it computes the values such as water level percentage, applies all the necessary control rules. Third layer is a network means connectivity. The Wi-Fi module acts as a network bridge. It communicates securely with Blynk cloud server using standard IoT protocols like MQTT or HTTP. Fourth layer is an application means user interface. Finally, the users interacts with the system through Blynk app. This is dashboard used for monitoring the data and sending back control commands. Next, we will see the core functionality and bidirectional control. Here, the project implements three core functionalities. First one is a water level tracking, second one is a temperature monitoring, and third one is a remote pump control, which is a bidirectional control component. Let's see. First one is a water level tracking. Data from the ultrasonic sensor is processed in MCU to calculate tank's percentage full, which is then displayed on blink gauge, enables proactive altering on low levels. Second one is the temperature monitoring. Ambient temperature is continuously logged and maintained on blink chart for trend tracking, providing the foundation for environmental automation. Third one is the remote pump control. This is a bidirectional control component. The user sends command via Blynk App. The system remotely toggles the simulator water pump status on off. Next one is the bidirectional control. We will see how the bidirectional control works, means virtual pins. The core of the cloud communication is a virtual pin abstraction. This decouples the application data from physical hardware pins, means device to cloud monitoring. We use blink.virtual hash v hash data send sensor data like temperature or water level to the cloud. Second is a cloud to device control. Remote commands from user trigger to the specialized blink write vhash function in C++ code. This function contains the logic to toggle output like pump or relay. So next one is a live demonstration setup from code to real-time control. In the live demonstration, we verify two key objectives. First is the data integrity, monitoring the flow, and second is the bidirectional control flow. Here, simulation platform we use the PicsimLab, I have already told. And second, for control interface, I have used the Blynk Web, means mobile app, for to display all the incoming data and control the remote buttons. This is the Arduino, and this is the old spare parts which have used in the project. And this is a serial remote tank, and here is a its output is showing how much its level is. And here we use the Blynk IoT for data integrity. We also told the cloud to device control flow is a functional which confirms this logic. And this is the screen of my mobile phone where I have created these buttons in Blynk IoT app to control my whole process. So I will show the whole live demonstration of this project now. This is the Arduino. For starting this, we need to give it hex file because it cannot understand our code which is written in Arduino IDE directly. So for that we need to convert the whole code into the uh, export binary file that will give us the hex file, and we need to load here. After loading here its whole output we will see here. This is a CLCD, this is the LDR sensor, this is the LED, this is the heater cooler system, and this is a Ethernet shield. Here, first line shows the temperature and second shows our water level tank. So, first we will see the heater and cooler system. I will control this through my mobile app. If I start the heater will be on, will show here, and its value will be get increased, mean temperature will be get increased. And the data from here to mobile app, the whole time, means sending this data to the app will be the 1 second time. See here, temperature I have gone to the 31 degree. I will off the heater and start the cooler. When I start the cooler, the fan gets started and its temperature will be go decrease. And here the cooler is started is shown. This is a heater cooler system which I done in here. And we will see now our serial water tank. Here we create the virtual pins. For that, the serial port here connected to COM2, and in Arduino we have created the serial port. I will show. We have created the serial port connection. First is the COMP1 which is connected in Arduino, and for serial tank here connected to COM2. When I start the inlet valve, water tank will get filled. When I stop, it will stop. And after starting the outlet valve, water will be flow. And here we see its level. Also we can see here in CLCD. Here also, if inlet valve gets started by itself, by mistakenly by user, here we connected the ultrasonic sensor. After reaching this level, this will get easily activated and stop the water automatically. Here we can see the inlet flow is the 3000 liters, and I want to drain out the all water. I will stop the inlet valve and start the outlet valve. The water will go, and its level directly show here also in CLCD. So let's move our PPT. So we saw hold the data integrity, monitoring the flow. We confirmed that changing the simulator sensor value in PicsimLab immediately resulted in correct update on Blynk gauge on mobile app. Here, and bidirectional control means controlling the flow. We show that clicking button on Blynk app instantly toggle the status of simulated pump or relay within PicsimLab. I have already told this. This confirms the robustness of command flow. So we will next move to the next slide. Here is a future scope. Moving forward, there are two main areas for the group. First is automation implementation, and second is a hardware migration. Here, adding autonomous threshold logic within microcontroller code itself. For example, pump should turn up automatically at 95% because when it reaches to the maximum level, means here through ultrasonic sensor, this will stop. But if we want to stop it at its 95% level, we can add or implement more something that or upgrade it. Water level turn on at 20 degrees Celsius. Also this means automatically turn up at 95% level and 20% level on at that time. And second one is the hardware migration. The ultimate step is the transition the validated optimized code base from PicsimLab simulation environment to the dedicated physical ESP32 device for production ready solution. These are the two main areas that will be get grouped. And let's move to the conclusion. In conclusion, this project demonstrated two critical achievements: full stack IoT proficiency, the successful integration of fundamental embedded C++ programming with commercial grade cloud platform like Blynk. Second one is the simulation and debugging mastery, verification of system integrity using hardware-in-loop simulation in PicsimLab, which is a critical skill for any embedded developer. So after this, thank you. I am now happy to tell that I have gained so much information, so much knowledge in this internship. Also develop a small project in this through help of Jayalakshmi ma'am. Ma'am told us so many things in this internship. Also solve our so many doubts. Also taught everything in easy way, and we understand this. So I would like to thank MX Technologies for giving me this opportunity, and I would like to thank you again. I will conclude my project. Thank you, everyone.